Hi, Rob here. This is Confessions of a Crap Programmer, episode 6, and this one is mainly about making compiled sprites. In the last episode, I had a routine to draw a red square without transparency. The pixel data was hard-coded directly into the routine, and this is essentially what a compiled sprite is. A compiled sprite is a faster way to draw graphics, but it does have a few downsides. For example, converting all the graphics for a game by hand like this would be extremely time-consuming. So you need some kind of process for converting your pixel data into the compiled sprite automatically. A compiled sprite is also several times bigger than the raw pixel data on its own. So if you want to be more efficient with memory, you could keep all your graphics as raw pixel data and then just convert sprites into a temporary buffer when you need them. Now, on the Sam Coupe, we're blessed with 0.5 MB of RAM, or at least 256K, and so I've found that a bit of optimization is enough to keep my sprites small enough to just store them in memory as is. So, for making compiled sprites, what we're talking about is writing a program that writes a program, which is very cool. This makes you feel like a real programmer. And since doing this with compiled sprites, I've also had a go at using it to speed up my games by generating code into a subroutine before the game begins to avoid having to search through arrays of data during the game loop to find specific values for a particular level. I can talk about this in another video sometime because it's easier than making a sprite, but very effective. I'm going to make a simple example program just to cover the basic process, but first I want to explain what we're going to do for anyone who is a complete beginner, because if someone had done this for me back in the day, I wouldn't have got frustrated and given up on programming for such a long time. If you remember typing in pokes for your ZX Spectrum, then you would have seen several data statements with a block of numbers like this. As a kid, I had no idea what this was or what it did. It was just a complete mystery. It turns out that most of the time that data would be an actual piece of program code that would be patched over the game code in the right place to give you infinite lives or whatever. And if we use the Z80 code text file I mentioned in episode 3, we can find out what these instructions are and start to translate that data statement back into something that can be read and understood more easily. I have to convert those values to hexadecimal first, and then you can see right away how this works. The first value, 3E hex, corresponds to the load A with an 8-bit number instruction, and that the next value, OE hex, is the value to load into A. The next value, 32 hex, corresponds to the load address with A instruction, and the next two values are the address. It's important to note that for the 16-bit values, these 2 bytes are in reverse order due to the Z80 being little endian. This will come up again in a few minutes when we look at stack pointer drawing, but for now we can go through all the data like this and slowly recreate the program. The sprite compiler is going to go through the same process as this, but in reverse, turning the drawing routine into a string of numbers with the pixel data in the right places in the resulting code. So here I've taken the drawing code for a non-transparent sprite from the last episode, and I've edited it to just help with getting the values I need. You'll see that I've simplified the routine, removing the conditional jump that handled which routine to use for doing single pixel movement, and I've just written out the block of code for drawing one row of pixels, as we can use a loop in our compiler to cycle through the other rows. I've added the values for each instruction so it's easier to see what I have to do, Some instructions need a little bit of effort to work out. For example, the rotate right H instruction requires the second byte to be modified to get the right value for the H register. This table from the Z80 code text file explains what to do. We need H, so that's 18 hex plus 4, which makes 1C hex, and it's 1D hex for the L register. So this is the program I've put together. It's using the same template program that I used in episode 3, with the only difference being that I'm keeping interrupts disabled. At the bottom, I've got the array of data for the 7x7 pixel red square from the last episode, and I've created a buffer for the finished compiled sprite data. For the compiler itself, first I made some pointers to the data. DE is set with the address to the sprite data, and HL to the output buffer. Then it's just a case of adding each value for the first part of the drawing code up to the first row of pixels being drawn. So first load BC with 125 with the values for the 2 bytes reversed for the 125. Then the set carry flag, rotate right H, rotate right L, and I'm just adding the value and then incrementing HL, nothing to it. Now I set B to 7 for the loop counter and create a label for the loop. From there, it's just a case of adding the load HL instruction and then reading in a byte of graphic data from the sprite array. HL and DE get incremented every time a byte is written to HL or read from DE, and finally the increment L instruction gets added. That's the first byte of pixel data processed, and as we have 4 in total for the row, I just copy-paste this block to make 4 of them. The last byte in the row doesn't do an increment L, so I changed the output byte to 09 hex for the add HL with BC. That's the loop completed, and after that we could just add the return now, but I've gone back 1 byte to remove the last add HL with BC as it isn't needed after drawing the last row of pixels. Add HL with BC only uses 1 byte, so I just needed to decrement HL and then overwrite it with the return. So back at the beginning of the program, after setting the stack pointer, I've put a call to the compile routine and then a halt instruction. I can compile this and have a look at the output in SimCoupe. I'll take a note of the address of the output array so we can find it in memory to make sure it looks okay. Once it's been run, I can go in and find the output buffer at D7 hex. As you can see, it worked okay, and a nice unrolled compiled sprite has been created. So that's all there is to it. The routine for creating a compiled sprite with a fixed size and no transparency is very simple, but from here the routine could be expanded to handle any sprite size or to do something completely different, like stack pointer drawing. With the stack pointer, you can draw 4 pixels at a time, and the stack address gets moved automatically with each push, which also saves a few t-states. The bricks in the Atari ST version of Arkanoid 2 are 16 pixels wide and 7 high. 16 divides evenly by 4, so they're the perfect size for drawing with the stack pointer. This is the routine for drawing the red brick in the SamCoupe source code. As you can see, the first thing I do is preserve the current stack pointer address, and because the routine is going to change the stack pointer, you need to be able to return it to its current address, and you'll need to be certain that an interrupt won't occur while the routine is being run. This won't be a problem if you're doing all your drawing immediately after an interrupt occurs, but otherwise you will want to disable them before calling the sprite. So you can see I load the current stack pointer address into a load stack pointer instruction at the end of the routine. When you draw something with the stack pointer, you have to draw it backwards, by which I mean starting from the end of the last row of pixels. The first thing I do after converting HL from the raw XY coordinates into the screen address is to use DE to add exactly the right value to move to the right place on screen. This is the brick sprite with some grid lines to make it easier to see what's going on. For the brick sprite, we need 6 times 128 to get to the right row plus the width of the sprite in bytes, which is 8. So the stack pointer is set to this byte here, just beyond the last pixels on this row. BC is set to -128, so it can be added to HL to move up the screen by 1 line after drawing each row. Now the actual drawing begins. The stack pointer is given the screen address from HL, and then the pixels to draw are loaded into DE and pushed onto the screen. When we use the push instruction, the stack pointer moves backwards through memory or right to left on screen by 2 bytes before adding the value being pushed to that address. As we saw before, the pixel pairs go into DE the opposite way round than you would expect. It's easy to get caught out, so beware. As you can see, I'm saving a few ticks here and there by just updating the registers that change between each push. All of these little savings make a difference, but writing out sprites by hand like this is still time consuming even with a smaller stack pointer routine. So that's it for this episode. I hope this has been helpful to someone. As always, I'd be interested in hearing about what I'm doing wrong. How does everyone else do this stuff? I found very little online to help me when I was trying to work it out. If you want to see more tutorials like this, or if you'd be interested in supporting the development of my Sam Coupe projects, some of which I'll also be porting to the Spectrum Next, Atari ST and Sega Master System, you could consider supporting the Wubsoft Patreon, which is now up and running. Until next time, thanks for watching.